All right, hello AP class. This is your lesson for day 54, Friday, November 8th. It's due a week from today, and it's on a resonance and formal charge. So a resonance structure, first question is, what is a resonance structure? A resonance structure is an alternate configuration of a molecule that can occur when you follow the Lewis dot structure rules that we learned yesterday. So if you get two alternate structures that are different, even though you followed the Lewis dot structure rules, that's called a resonance structure of a molecule. And what we do then is we use formal charge to determine which of these structures is the one that's preferred in nature. In other words, which one will you actually find in nature? So let's go ahead and define that. So a resonance structure is go ahead and write this out. So it's just an alternate structure of a molecule. And then write the formula for formal charge on an atom and explain what it is used for. Well, it's really the formal charges combined of all the atoms in a molecule. So I'm going to actually answer that question. The combined formal charges of Okay, so the combined formal charge of all the atoms in a molecule, which will determine which structure is preferred in nature. Now you have to figure out the formal charges for each atom one at a time, and so we'll demonstrate you'll learn how to do that in this lesson. The formula is simply the number of valence electrons in a particular atom. E minus is the abbreviation for electrons, minus the total number of non-bonding electrons, that you would also say lone pair electrons, but it's not the number of lone pairs, it's the total number of electrons in lone pairs or non-bonding electrons, minus the bonding electrons. Again, this will all become clear when you've worked a few of these. They're not that hard, and we'll get to those today. All right. So first I have you start off doing what we were doing yesterday, which is just to draw the Lewis structures of some molecules. So what I would like you to do is have your notes out and turn to page 7. This is Unit 5, Covalent Bonds. And you want to turn to page 7 of your notes. And on page 7, there are the rules for drawing the Lewis structures for molecules. So until you become proficient at this, what you should do is just go down this kind of like a checklist. Do each of the steps one at a time until you're comfortable with this, all right? So I'm going to assume you have that in front of you, so I'm going to set that off to the side. Well, I'll do the first couple here, but then I'll set that off to the side. You can do those. So the first thing you do is you determine the total number of valence electrons. So we come over to SiCl4. So Si, there's one Si atom here. Okay, and then we look for silicon, And it is in the fourth position from the left, which is in the third row, 1, 2, 3, 4 positions from the left. So that means there's 4 valence electrons. So that equals 4 valence electrons for silicon. Then we have chlorine. We have 4 of those. And it is in the 7th position in the third row. 1, 2, 3, 4, 5, 6, 7 for chlorine. So there's going to be 7 valence electrons for chlorine, so that's a total of 28. And when you add those, you have 32 electrons. E minus is electrons. So what that means is when we create this Lewis dot structure, we need to have 32 dots. While you're getting started with this, while you're new at this, I want you to use dots and not lines so that you can actually count them and you're very clear on what's going on here, okay? All right, so let's continue on. So the next rule says, draw the structure with the least electronegative atom where the least electronegative atom occupies the center of the molecule, and it's usually written first in the formula. So if that's true here, then silicon would be the least electronegative atom. So if we go back to our periodic table, or what you should have out also is your periodic table of electronegativities. So we can see that if you look at the periodic table of electronegativity, silicon has an electronegativity of 1.8 and chlorine has an electronegativity of 3. So that means silicon would be in the middle of the molecule. There are some exceptions to this. Again, in chemistry, a lot of times there's going to be exceptions to rules, but this is generally the case. The other way you could have known is that the electronegativities get higher as you go up the periodic table and to the right. And since silicon and chlorine are in the same row, and chlorine is further to the right, it would have a higher electronegativity, assuming you didn't have this table to tell you what they exactly are. So that means we're going to put silicon in the middle. And for chlorines, since you don't know the shape of the molecule, we haven't talked about that yet, you're just going to put them around in kind of a symmetrical fashion. So I'm going to put them around all 4 of those, okay? All right, now we move on. Rule 3 says, or Rule 2A rather says, hydrogen and fluorine occupy outside positions. There's no hydrogen or fluorine in this, so that rule doesn't apply. Rule C does, however, connect the outside atoms with the central atom using single bonds. So remember what's happening in a covalent bond. The chlorine is contributing an electron to this bond. The silicon is contributing an electron, and they share these 2 electrons right there. And that's going to happen in all 4 cases. Chlorine contributes an electron, silicon contributes an electron. Same thing here, and same thing here. So we follow the rule, and we've connected all of the outside atoms with the central atom using single bonds. And we've used 8 of our electrons, but we still got a long way to go because we have to use 32. So let's see what the next rule says. It says place the remaining electrons to create octets. And what I would do is be sure you always starting with the outside atoms, not with the central atom. Don't place them on the central atom first. Do that with the outside atoms. So starting with outside or terminal, if you want to use that word, atoms. Okay, so add that little note there. So here we go. It's going to be a lot of them. I'm going to put a couple here and leave myself space there, but that's okay. Okay, so now this chlorine has an octet. Now this chlorine has an octet. An octet and an octet. So each chlorine has 8 electrons, octet, 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 octet. What about silicon in the middle? Well, in doing that, we created an octet for silicon. It has 1, 2, 3, 4, 5, 6, 7, 8. Remember, when you create covalent bonds, the bonding electrons count for both of the atoms that are involved in that bond. So these 2, for example, count as 2 for silicon, but these same 2 count as 2 for chlorine. So that's the principle of covalent bonding, is they share electrons, and each of these atoms thinks that these two electrons belongs to it. Silicon thinks these two belong to it, and this chlorine thinks that these two belong to it. All right, so does silicon have an octet? Well, it sure seems to. 1, 2, 3, 4, 5, 6, 7, 8. So everybody has an octet. So the two rules you want to follow is, one, assuming it's not an exception to the octet rule, and we'll get to some of those, is every atom, I should say, has an octet. Okay. The second rule is you must use all of your electrons. So in this case, all 32 of these electrons. The fact that I just said in covalent bonding you kind of double count these, you don't double count them as part of the 32. You literally have to see 32 dots on the page here. Okay, so let's see if we do, well, we got 8 here, we have 8 here, 8 here, 8 here, so that's 32. Everybody has an octet, so this is the final Lewis dot structure of the molecule silicon tetrachloride. Okay, let's go on down to PF3. So we're going to draw a line here so we keep these separate. So phosphorus, there's one phosphorus in this molecule, and phosphorus has 5 electrons, valence electrons. Okay, so we have 5 here, and then fluorine, there's 3 of those, and it has 7, so that equals 21, and if we sum those up, we have 26, so that means we have 26 electrons that we have to place. All right, so which is less electronegative, phosphorus or fluorine? Well, again, you can go to your periodic table of electronegativities. Phosphorus 2.1, fluorine 4.0. So that means phosphorus is going to be in the middle. So we're going to put that P, and we'll put the F's around it as symmetrically as possible. We only have 3 of them, so they can't go on all 4 sides. Okay, so we've placed those. Let's go back to our rules. So draw the structure, the least electronegative atom occupies the center. We just did that. We don't have a hydrogen and fluorine, so we can skip that rule. And then connect the outside atoms to the central atom using single bonds. Again, each fluorine is going to contribute an electron, and each phosphorus an electron, or the phosphorus an electron. Fluorine electron, phosphorus electron, fluorine, phosphorus. So that's a total of 6. Down here, that's a total of 6. I need to use 26. So the next thing we do is, it says 3, place the remaining electrons to create octets, and you start with the outside atoms. So don't start by putting 2 right there at the end of phosphorus to create an octet there. Start with fluorine. Okay, so here we go. So there's another 2, another 2, another 2. So this fluorine has 8, that's an octet. Octet, octet. So now let's count. Each fluorine has 8, so there's 8, 16, 24. So we've placed 24 electrons. We still have 2 more to go to get to 26, and we see that phosphorus does not have an octet. It only has 6 electrons, so this will be a lone pair, or a non-bonding pair of electrons up at the top of phosphorus. So now we've fulfilled our 2 rules. Every atom has an octet, and we've used all of the electrons, the 26 that we started with. So that's our answer right there. Okay, let's move on. Next to, whoops, got my line wrong. Next to the CS2. Okay. All right, let's go ahead, see again, start seeing if you can do these on your own, okay? Carbon, 1 times 4 valence electrons, 4th position over from the left in the 2nd row. That's going to give you 4. And S. And sulfur is the 6th position over from the left in its row, the 3rd row, and there's 2 of them. We need to multiply 2 times 6. and that's going to give us 12. So that means we have a total of 16 valence electrons that we have to account for in our Lewis structure. Yeah, and if you're not sure of the shape of a molecule, just draw the most symmetrical that you can. First, we have to identify which is the least electronegative. Just looking at a regular periodic table, you might not be able to tell because sulfur is further down, which means less electronegative, but it's further to the right than carbon, which means more electronegative. And if you look at this, it's a tie, 2.5 to 2.5. So if you ask me to guess, I would guess that you may draw the most symmetrical molecule that you can. So I'm going to put a carbon there, a sulfur there, and a sulfur there. If you're not sure that maybe it should have been sulfur, sulfur, carbon, when we get to formal charges, if you want, you can do a formal charge analysis on this and see if truly this is the proper structure. Okay, so we're going to keep going. So now the next thing that the rules say to do is to create single bonds between the central atom and the outside atoms. So connect the outside atoms with the central atom. Again, just use this list as a checklist as you go down for each one. So we're going to put a single bond there. So carbon contributed one of those electrons and sulfur contributed the other. So now they're shared. Again, remember the strong guy metaphor. These are two strong guys and they want each other's electrons, but neither one is strong enough to totally pull them away. So they end up sharing the electrons. And again, carbon thinks that these two belong totally to it. And this sulfur thinks that these two belong totally to it. On this side, same thing. Carbon thinks these two belong totally to the carbon, and the sulfur thinks these two belong totally to this sulfur, okay? All right, so we've taken care of 4, but we got 16 to deal with. So now we create octets around the sulfur. So we got 1, 2, 3, 4, 5, 6 more. And over here, octet. Okay, so what do we have here? We have 8 electrons here and 8 electrons here. So that accounts for all 16 of the electrons. The problem is this: while both of the sulfurs have an octet, the carbon does not. So we have to figure out a way to give carbon 8 electrons. It only right now has 1, 2, 3, 4. We have to give it 8, but we can't add any more because we've already used all of our 16 electrons that we're allowed to use. So the way we would do this one is, and it really doesn't matter which ones of these pairs that you choose, but you typically choose the one that's kind of makes it look more symmetrical. That's just kind of the convention. So I'm going to erase these two. So now we're down to 14. That means I have to write them back in again. I'm going to put them right here, and this is called a double bond. It's 2 pairs of electrons bonding. So we do that on this side, and we're going to do it on the other side. And there we go. Let me make sure this is really clearly erased so you know that those electrons are not there anymore. Okay, so now we still have 16, 8 on this side, 8 on this side, and now everybody has an octet. Sulfur still has an octet, and carbon has 1, 2, 3, 4, 5, 6, 7, 8, so it has an octet, so in each of the sulfurs. So this is our final configuration. It's a molecule with 2 double bonds on each side. Okay. Let's go down to D, and it's HOBr. Now this one's going to throw us a little bit of a curve, but there's a clue to how to write this one. If we follow the rules, we're going to write it so that the least electronegative atom is in the middle. Now, if we look at this, we see Br has a fairly significantly less electronegativity than oxygen does, and that would tell you that it should go in the middle. But the clue for us is that usually molecules are written, or their structure is, if they write the molecular formula in this order, then that's the way the molecule is arranged, the atoms in the molecule. So we're going to go ahead and assume that, even though it's breaking our rule. And you say, well, how do you know for sure? And the answer is, later on you can do a formal charge analysis when you've learned to do that and see if HOBr is preferable to HBrO. Hydrogen can never be a central atom, so that's not even one to consider. All right, so let's go ahead. We're going to connect. So we put it in the order we think it should be. And we're going to, hydrogen and fluorine occupy outside positions, so we do have hydrogen on the outside. And rule 2C rather, is connect outside atoms with the central atom using single bonds. So there we go, and there we go. Now notice that hydrogen, remember hydrogen's in the first row. It has one orbital, and the first orbital can only hold 2 electrons. So now that oxygen has shared one of its electrons with hydrogen, and hydrogen had one of its own to start with, hydrogen has a full octet. Even though it's not 8, and the word octet means 8, hydrogen has a full octet. It has 2, and that's as many as it can hold. So we're done with hydrogen. We can't add any more to hydrogen. Then the rule says we need to fill the rest of the atoms with octets. So since both oxygen and bromine are below the first row, they can handle 8 electrons. So we start with bromine, and we put them around here. And you know, I was in such a hurry to do this and talk about the HBr, I didn't do something I should have done, which is to count how many electrons I need. So let's go ahead and do that right now. And that gives us 14 electrons. Okay, so we're going to need to have 14 electrons. Right now we have 8 plus 2, we have 10. So now we're going to go ahead and put on, so since we need more, now we'll go ahead and start filling up the central atom. And we have 2 there and 2 there. Okay, so now we have 8 and then another 6 around here. That equals 14. And everyone has an octet. Bromine has 8 electrons, that's an octet. Oxygen has 8, that's an octet. And hydrogen has 2, which for it is an octet. So that's our final answer. All right, let's keep going. And now we're going to go to bromine pentafluoride, BRF5. Okay. So let's go ahead and figure it out, and fluorine is always the most electronegative, and our rule says that when we draw this, that hydrogen and fluorine occupy outside positions. So that answers that question right away. So we're going to draw this so that we can fit 5 BRs, so we'll try to draw it kind of symmetrically. So I'm going to put an F up at the top. The more symmetrically you can draw this, the better, and you'll see why in a minute when you see how many dots you have on the page. It's a little bit crazy. So there's a fluorine down there, and there's a fluorine over there. So it kind of looks like a star. Okay? All right. So the next thing is, it says, so the least electronegative does occupy the center. Fluorine is in a terminal or outside position. Connect the outside atoms with the central atom using single bonds. So here we go. There's 2. Again, bromine contributes 1, fluorine contributes 1. They share it. Neither one can take the other guy's electrons away, so they have to share. And there you go. Now, something funny about this. Bromine has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That seems to violate the octet rule. It has more than 8 electrons. It has 10. Well, this is an exception to the octet rule, and you're going to learn about these more in the next couple weeks, but for right now, just learn it at least this much. It's called an extended octet. And atoms in the 3rd row and below can form extended octets. They can actually have as many as 12 valence electrons. No more than 12, but they can have up to 12. In this case, bromine has 10. All right, so there you go. Now the next rule says, again, I failed to count my atoms, so let's do that. So bromine, we have 1 times 7. And for fluorine, it's also a halogen. It's right next to the noble gases, and there's 5 of those. And they also, again, you're counting from the left to right to see what position that holds in the row. Now, here is another issue to take up. We see that bromine is in the 4th row. It's way over here. Why did we say 7? Well, did we count these? You do not count the transition metals. They are never valence electrons, and you're going to learn about those in the next couple of weeks. For right now, though, you just have to understand that transition metals, anything in this, what I call the valley here, is not a valence electron. So in the fourth row, you have potassium, calcium, then you skip over to gallium, germanium, arsenic, selenium, and bromine. So bromine has 7, just as chlorine does, just as fluorine does. It has 7 valence electrons. All right, so you go ahead and do that. That's 7. And this is 35. It's a big number. And when you add those, you get 42. Yes, that means we're going to have 42 dots on the page, but when this is all over. So our next rule is, let's go ahead and make octets around all of the outside or terminal atoms, and since they're kind of odd angles, I'm going to try to do this as neatly as I can and put 2 there, 2 there, and 2 there. So this fluorine has 8. Okay, I'm going to put 2 here. Okay, octet right there. Octet right there. Octet. And one last one here. Okay, so you can count all those dots, but what I know is this. I know that I have 8 around each fluorine, and there's 5 fluorines, so that's a total of 40. But I need 42. So let's read the additional rules here. It says place lone pairs of electrons around outside atoms to give each an octet. We just did that. Okay, number 5, assign remaining electrons as lone pairs around the central atom. So we have 2 left, and it's getting a little crowded in here, so I'm going to just draw an arrow. So right next to bromine, not next to any of the fluorines. It's not between any of the fluorines and bromine. It's just on bromine by itself. It's a lone pair. It's not bonding. I'm going to draw 2 more electrons. I just put them out here so you could clearly see them because it's kind of a mess in there. So I now have 42 electrons, and everyone has an octet. Fluorine has octets, 8 electrons, and bromine has an extended octet. And remember, I said it could be as many as 12 electrons. So it has 1, 2, 3, 4, 5 pairs of bonding electrons. That's 10 electrons, plus 2 more lone pair. So bromine does, in fact, have 12 valence electrons, and that's that. All right, moving down here. And now we have BH3, and BH3 is also an exception to the octet rule for a different reason, though. It's not in the 3rd row or below. That's why I said bromine could be an exception. Boron has only 3 valence electrons. Whenever you have an odd number of valence electrons on your central atom, what do? You got only 3. It can only form 3 bonds. It can't form 4 bonds. So you may end up with less than 8 electrons. So let's go ahead and do this one. So boron is right here, and there's 1 boron, and boron has 3 valence electrons. Okay, hydrogen. There's 3 hydrogens, and each one has 1 valence electron. You add those 2 together, you get 6. So we need to have 6 total electrons. Okay, so the boron is going to be the central atom, so I'm going to put it right here. I have 3 hydrogens. Again, just place them as symmetrically as possible if you're not sure where they go. Right there. Okay, so that's how we're going to place those. And now we create single bonds between the central atom and the terminal atoms. So there's 1, 2, 3, 4, 5, 6. So we see that each hydrogen has a full octet. Each one has 2 electrons. Draw this a little more clearly. Each one has 2 electrons. Hydrogens are happy. They've got a full octet. Boron doesn't have 8. It only has 6. But we've used all the electrons we have to use. We've used 6. So this has to be our final answer. If this forms a bond at all, you may say maybe it doesn't form a bond at all. It does actually, though. And if it forms a bond, then it's got to form it with only 6 electrons surrounding boron, not 8. So this is the exception to the octet rule for boron, and boron frequently has that exception, okay? All All right, let's keep going. Okay, next one is ethylene. It's C2H4. So again, let's follow our rules. Determine the total number of valence electrons. So carbon, so there's 2 carbons times 4 valence electrons for carbon is 8. Hydrogen, there's 4 hydrogens times 1 for each. That gives us 4. And if you add those, you end up with 12 electrons total that we need to account for. Let me move over here. So how do you place this? Remember, we're trying to be symmetrical here. So which should be in the center? Well, hydrogen has a lower electronegativity than carbon. However, it can't be a central atom. It must be a terminal atom. That's one of our rules. So that means hydrogen has to always be on the outside. So what we're going to do then is since we have 2 carbons and they're both equal to each other, one is not superior to the other, they're both going to be central atoms here. And since I have 4 hydrogens and I want to place them as symmetrically as I can, rather than I'm going to put one here and one here, and then one here, and then one here. Okay, so that's probably the best way to draw it. Another possibility you might have done is drawn them off at an angle this way, an angle that way, an angle this way, an angle that way. That would have been nicely symmetrical too. But let's just keep it simple, make everything, horizontal, vertical. Here. Okay, so the next rule says we need to connect the central atoms with the outside atoms. All right, so we're going to have 2 here. And the other thing we're going to do is we got to put a bond between those 2 central atoms. So although that wasn't explicitly in the rule, it's part of the rule too. You got to put a single bond there. Okay, so we bonded everybody together who's in that molecule. So how many electrons have we used? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We need to use 12. We need 2 more. We see that hydrogen is happy because all the hydrogens have a full octet, 2 electrons. The carbons, however, only have 1, 2, 3, 4, 5, 6 on this one, and the same on the other one, 6. So what we can do with those extra 2 electrons is just stick them in the middle, create double bond there, and now both of the carbons, or each of the carbons, has an octet. That has an octet, this one has an octet. Remember, they share these 2. Each of the carbons thinks that these 4 electrons belong to it. This one thinks these 4 electrons belong to it. So everybody's got an octet, and we've used all 12 electrons, so that's our final answer there. Okay, so let's wrap up this part of the assignment with one more Lewis structure. It's ammonium, NH4, and so what we do is count our electrons. So nitrogen, there's 1 of those. Go to your periodic table. It's the 5th position from the left in the 2nd row, so there's 5 valence electrons, so that's 5. Hydrogen, there's 1 of those, and there's 4 of those, and each one has 1 electron, so that gives you 4 right there. And then the plus charge, what does that mean? It means it ionized. It has 1 less electron. 1 of the electrons left it. Okay, so what we're going to do then is just simply put a negative down here, a -1 right there. Just put a -1 right there, and that's an E minus that's gone away. So now it has a positive charge, but you also have to factor that into counting your valence electrons. It didn't necessarily go away. Well, it went away from the hydrogen, but that's not important for our purposes. We just want to know how many total valence electrons we have. So 5 plus 4 minus 1 is 8. So we need to account for 8 total electrons. Okay, this one's pretty obvious as far as configuration. It's NH4. The hydrogens have to go on the outside. Okay, next thing is we connect everybody with single bonds. So single bond. Okay, and we see that we've used 8 electrons here. Everybody has an octet. Hydrogens have 2, nitrogen has 8. We're done with that problem. That's all there was to that. Okay, let's go to question 4. It says indicate whether the bond formed between each of the following pairs would be pure covalent, polar covalent, or ionic. So what you need to do for this is get your notes out, and there's a table on page 7 right here, and it simply tells you that if the electronegativity difference between the two atoms is less than 4, that means one of them is not really any more electronegative than the other. They're both pretty close. That means one of them is not going to be pulling more on the electrons than the other. Then it's a nonpolar covalent bond. If it gets to 0.4 to 1.8, and by the way, these numbers may be slightly different in different books. These but these are pretty good numbers to work with. If it's in between these two numbers, it means that one of the atoms is pulling harder on the electrons than the other. Not hard enough to be able to actually pull them away from the other atom, but hard enough to be able to pull them over closer to the more electronegative. So if your difference in electronegativities is between these two numbers, it's a covalent bond, but it's a polar covalent bond. One end is going to be more negative, one end is going to be more positive. Finally, if the differences are very large, greater than 1.8, then that means essentially one of the atoms has totally pulled an electron or electrons away from the other atom, and that becomes an ionic bond. One of them becomes an anion and one of them becomes a cation. So just using this table, go ahead and answer these questions. So I'm going to assume you're seeing that as I'm seeing it as I write these. So indicate whether each of the bonds is the following. So carbon and bromine. So you should have out your periodic table of electronegativities. So carbon is 2.5, bromine is 2.8. You're always subtracting the bigger and minus the smaller, because you're just interested in the numeric difference. So it's 2.8 minus 2.5 equals 0.3. That's less than 0.4 that was on the table on the notes. So that's going to be a nonpolar. Okay, bromine and fluorine. So we'll come over here. Fluorine is a 4.0, bromine is a 2.8. Now again, I'm not doing it, I'm doing it in reverse order here, simply because we want it to be a positive number. We're just interested in the difference. We're not interested in which side was which. So you add those two together and you get 1.2, and that's going to be polar. It's in between 0.4 and 1.8, so that's going to be polar covalent. All right, phosphorus. Phosphorus and arsenic. So we look there. Phosphorus is 2.1, arsenic is 2.0, very close together. So that's going to be nonpolar. Okay, next one is strontium and sulfur. Okay, so strontium is strontium is 1, sulfur is 2.5. Okay, so we've got sulfur is 2.5 minus strontium is 1.0. You subtract, you get 1.5, and so that's polar covalent. Okay, so who notices something unusual there? Think about it. Okay, now that you've thought about it, what's unusual here is strontium is clearly a metal. Sulfur is clearly a nonmetal. Metals and nonmetals, we have always said, form ionic bonds. Yet using this, we're saying it's not ionic, it's polar covalent. So which is right? The answer is this is really the way that you should tell. There's not a sharp division between ionic and covalent bonds and polar covalent bonds. It's kind of a loose, fuzzy difference. So this is telling us polar covalent, so strontium and sulfur would be polar covalent bonds. even though one is a metal and one is a nonmetal, and for the entire course we've been saying that that would create an ionic bond. It's fairly close to an ionic bond, but not really that close. So this is actually a polar covalent bond. Okay, let's continue on. Potassium and oxygen. Okay, so potassium right here at 0.8, oxygen 3.5. That's kind of a easy one. That's 2.7, and that's clearly an ionic bond. Okay, finally, nitrogen and boron. Okay, so nitrogen is 3.0, boron is 2.0. That equals 1, and so that's going to make it polar. All right, and that's all there is to that exercise right there. Okay, now we get into the serious part of this lesson. It's going to take a little bit of time. It's important that you get good at these, and hopefully by the end of this lesson, you'll know how to do these very, very well. All right? Okay, so NCO. What we're going to do is we're going to draw that molecule in 3 different ways. The first way that we think it really should be drawn is based on the chemical formula there. It's NCO. So we're going to draw the N here. We need to create the Lewis structure, and then we're going to analyze the formal charge. So N there, C there, O there. So let's go ahead and figure out how many electrons we're working with. So N, there's 1 nitrogen times 5 electrons is 5. Carbon is 1 times 4 is 4. Oxygen is 1 times 6 is 6. And then we have to add an electron there because it's a negative charge, and that's going to equal 1. It's 1 more negative charge there. So that's 9 plus 6 is 15, 16. So there's 16 total electrons. Now we're going to do the Lewis structures a little bit faster here, okay? So here we go. We are going to place single bonds between the center and the outside. That's good. Now we're going to create octets around the outside atoms first. And we can see that we have 8 and 8. We've used 16 electrons. The problem is that carbon only has 4. 1, 2, 3, 4. So we have to give carbon 4 more electrons without adding any new ones. We just have to take some from some other part of the atom. So how do we do that? I think you know this one by now. If you don't, think about it for, stop the video, excuse me, and think about it for a second. Okay, and what we're going to do is we're going to take these out here, erase them, and we're going to create double bonds there. And we're going to take these 2 here and erase them and create a double bond there. So now nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. Carbon has 1, 2, 3, 4, 5, 6, 7, 8. And oxygen has 1, 2, 3, 4, 5, 6, 7, 8. And we've used 16 electrons. So that's a perfectly valid Lewis dot structure. Now we're going to do another one. Now we're going to violate one of the rules on purpose here. We're not going to put the least electronegative atom in the middle. We're going to put one of the others. What if we made a mistake? What if we said, I think nitrogen should be the central atom? Well, these numbers are still going to apply. This is still the total number of valence electrons. But I'm going to go ahead and write this molecule down here with nitrogen in the middle. I'm going to put carbon on the left side. Okay, so we have carbon, nitrogen, oxygen. And if you think about it, the electron configuration up here has to be the same. They all take 8 in their octet. So I'm just going to go ahead and put 2 here on the carbon. 8 here on the carbon. Okay, and then over here on the oxygen, same thing. So it's the same electron configuration you have up there, but now I have nitrogen in the middle. So you'll see this also follows our rules for Lewis structures, except for the one that we didn't put the least electronegative in the middle. But we're going to see how formal charge could help us deal with that one, okay? Finally, we're going to do one down here. We're going to put oxygen in the middle just to see what happens. And again, we're still dealing with 16 electrons, so we're going to go ahead and create double bonds here and here. And so again, except for that one rule, let me get on screen here. Except for that one rule, these are all perfectly valid Lewis structures. They use all the electrons and they create octets for everybody. So here's where formal charge comes in. It's a lot of arithmetic, but you'll get to where you can do it very quickly. So the formula we wrote on the very first page was to get the formal charge on each atom, you take the number of valence electrons. I'm going to abbreviate this a little bit. Valence E minus the number of non-bonding electrons, or the lone electrons, the ones that are not in between the carbon or the nitrogen, the one that are not in the middle there, in other words. Non-bonding minus the number of bonding, minus 1/2 the number of bonding electrons. So let me make that correction. And again, I'm just writing kind of shorthand here. Number of bonding E minus. Okay, and that's E minus 2. Okay, there you go. There's your formula. All right, so let's do this. We're going to do this 9 times. One for each of these atoms all the way down here. And then we're going to see how they work together to help us determine and what the rules are for determining which of these would be the actual molecule that you'll see in nature. 2 of them you'll never see in nature. 1 of them you will. Which one? Okay, so let's do this. So we're going to start. We're going to just start in order and go from left to right here. So for nitrogen, nitrogen has 5 valence electrons. You get that from right there. Okay, minus. It's the number of non-bonding electrons, not the number of lone pairs. So there's 2 lone pairs here, but there's 1, 2, 3, 4 electrons that are not bonding with anything else. So there's 4 non-bonding electrons, and then you subtract 1/2 the number of bonding electrons between nitrogen and carbon here. So there's 4, so you take half of 4. So we have 5 minus 4 is 1, and then 1/2 of 4 is 2, so 1 minus 2 gives you -1. Next, let's keep moving. Carbon. Let me write down which one we're doing on each of these. Carbon is right here. These are not electrons, they're just a colon, okay, to separate this. All right, there you go. All right, so carbon has 4 valence electrons. None of its 8 electrons are non-bonding. They're all bonding. 4 of them with oxygen, 4 of them with nitrogen. So your non-bonding is 0. And finally, your bonding electrons for carbon, there's 8 of them in all, so you take half of 8. So 4 minus 0 is 4, half of 8 is 4, so 4 minus 4 equals 0. Keep moving. Oxygen. Stop the tape at this point if you get the concept, and do the rest of them on your own, and then just compare rather than copy. Okay, oxygen has 6 valence electrons. It has 1, 2, 3, 4 that are non-bonding. And then it has 1, 2, 3, 4 that are bonding. So 6 minus 4 is 2, and half of 4 is 2. So 2 minus 2 gives you 0. Okay, what are we shooting for here? We are shooting for, one thing you're going to find is we want to look at the combination of these 3 formal charges on each of the atoms. We're shooting for a number that, first of all, it's got to be -1. If you add these up, it's got to be -1 because we have a negative ion, an anion. So we have to end up with the same charge here that we have on our ion here, which is a -1, because you see the minus sign there. Okay, so we did that. Other than that, we want the numbers to be as close to 0 as possible. So 2 out of the 3 numbers are 0, and one of them, it has to be a -1 because I told you we have to have a -1. So this is as close to 0 as you can get. Okay, so let's contrast that to what you're about to see. Let's come over here. Now we got carbon, and now we're going to do this one. Carbon has 4 valence electrons. It has 1, 2, 3, 4 that are non-bonding, minus 1/2 of the bonding. It has 1, 2, 3, 4 of those. So 4 minus 4 is 0, and then half of 4 is 2. So 0 minus 2 is going to give you -2. All right, next is nitrogen. All right, so nitrogen has 5 valence electrons, minus it doesn't have any non-bonding electrons in this particular configuration. And then 1/2 of the bonding electrons, which is 1, 2, 3, 4, 5, 6, 7, 8. So that's 8, half of 8. So 5 minus 0, half of 8 is 4. So 5 minus 4 gives you 1. Finally, oxygen. Okay, so oxygen, and we have 6 for oxygen. Minus, oxygen has 1, 2, 3, 4 non-bonding electrons. And then it has 1, 2, 3, 4 bonding, so it's half of those 4. And that equals 6 minus 4 is 2, and half of 4 is also 2, so 2 minus 2 is 0. So these are the 3 numbers we get here. You'll notice that they still add up to -1. If they don't, you made a mistake in here somewhere. They have to. But which set looks closer to 0? This one does. It's got 2 zeros and a -1. Almost think of it like, oh boy, I don't know if I want to use this example. It's almost like a standard deviation from 0, if you understand that concept. If you don't, I'm sorry I said it. It's how spread out are these numbers from 0. These are all very close to 0. These are more spread out from 0. And that's kind of the way you want to look at that, okay? How about this one? Let's finish up with this one here. Carbon. Okay, so it's 4 minus over here is 4 minus half of the bonding electrons to oxygen is 4. So 4 minus 4 is 0. Half of 4 is 2. So 0 minus 2 is -2. Oxygen is our central atom for this one. So oxygen is 6 minus, there's no non-bonding electrons in that central oxygen, minus half of the bonding electrons, which in this case is 8. So half of 8 is 4. So 6 minus 4 is going to be +2. And finally, nitrogen has 5. 1, 2, 3, 4 of them are non-bonding. And 1, 2, 3, 4 of them are bonding, half of those. So 5 minus 4 is 1, and half of 4 is 2. So it's 5 minus 4 is 1, minus 2 more is -1. And again, if you look at these 3 numbers, they have to add up to -1, and they do. -2 plus 2 minus 1 gives you -1. So all these add up to -1. That has to happen. But again, you'll notice these are way off from being 0. These are kind of off from being 0. These are the closest to being 0. So this one is our actual molecule that we would find in nature, with carbon as the central atom. Okay? Hopefully, if you practice the rest of these will come through pretty well. What I'm going to do is wrap this video because we're at 53 minutes. So I'm going to put the rest on a separate video, and I'll continue that. And go ahead and get this one published. Right now it's Saturday afternoon, so I want to get this up for you. Okay? All right. So you'll be looking for the additional videos rather to get posted.